Okay, welcome Jack and Sophia, Marina, Marquette, and Liz, and welcome Roxy. Let's jump right to the quiz. Okay, so here's the quiz. And question 1 is, are Tahoe second homeowners more likely than Tahoe locals to leave their trash in canisters that the bears can get into? The Tahoe Bear League observed the neighborhoods and found that 97 of the 351 second homes had trash that the bears can get into, and 136 of the 612 locals' homes had trash the bears can get into. Use a 5% level of significance. Okay, so first thing is state the null and alternative hypotheses for the corresponding hypothesis test. Okay, so what we have, the first thing is for null hypothesis, hopefully you all get this part, and that is it always starts with H naught, colon. Okay, so hopefully that was an easy part for you. Now we have to look at the first thing is this a question about means or proportions? Is this about means or is this about proportions? Yeah, this is about proportions. And notice that we're comparing two proportions. So there's going to be two different proportions, and in particular, let's just call them P. So we're looking at second homeowners versus locals. So how about PS equals PL for the proportion of second homeowners that the bears can get into their trash versus the local proportion of locals where the bears can get in the trash. And there's the population proportion. Okay, then there's the H1. That's going to be PS. Okay, and then what is the inequality? Is it greater than, less than, or not equal to? Yeah, it's okay to say P1 and P2. I just like if I can, if it's not the same letter. If I use letters, then I remember which is which. With 1 and 2, it's a little harder to remember which is which and which is which. But 1 and 2 are fine. Not equal to, on the other hand, is not fine. What's the key word here? There's one word that tells you what we do, what it needs to be.
More likely.
Yeah, or the one word is more. So when you see a word like more, then don't write not equal to. It's greater than. Any questions on that? PL. Any questions on the part A to this? Okay, so always read through. I try not to hide it. I try to make sure it's very visible, the key word, but you have to look for it. And the word more is definitely there here. Okay, now write down the test statistic and the p-value. So we need to go to the calculator. And what test is this one? Which number?
19.
Yeah, there's 19. We got two proportions. We had a PS and a PL, or P1, P2, whatever you want to call it. And then it asks us for, the important things. So we need to get the first sample size. And let's scroll down a little bit. So notice the first sample is 97 over 351. So the sample size was 351. And 97 were the number of successes. Okay. In this case, the bear is becoming successful. The second sample was 136 over 612. So 612 and 136. we wanted it to be, again, it's a greater than. So we go up to greater than. Confidence level doesn't matter. I can just hit calculate because I don't need a confidence level for this one. All right, the test statistic is what? So to make sure everyone gets it. It's not tricky or anything.
Z, 1.8.
Yeah, let's get 1.89. Okay, because you should always round. Okay, and I wanted to mention this in particular because, you know, last week you had your test. Not all of you wrote down the test statistic when I answered it, when I asked for it. So let me write down test statistic was Z is equal to 1.89, and the p-value was equal to 0.03 is good enough for me. Any questions on that? Okay, we're using a 5% level of significance. So what does that tell you when the p-value is 0.03?
It's statistically significant.
Yeah. So we can say there is statistically significant evidence to conclude that and I want to mention an important word. There's a couple choices. So we have to make sure that we were referring to the entire population, not to the sample. So you can't leave it vague. You can't say sample. You must refer to the population. Okay. So we can say the population proportion of, and now we can look at it, Tahoe second homeowners. And now let's read some more. That leave their trash in canisters that bears can get into. So I'll copy and paste that. Is greater than the population proportion of, and now what we're comparing it to, Tahoe locals. So I'll copy and paste that and adjust it a little bit. Change the 2 to that leave their trash in canisters that bears can get into. And that's it for the first question. Any questions on the first question? Okay, let's look at the second question. Do male counselors spend less time working with each student than female counselors? 8 male counselors and 8 female counselors were observed. Use a 5% level of significance. The minutes per student are shown below. All right, so we want to state the null and alternative hypotheses. So I'm going to write H naught. Is this about means or proportions?
Means.
Yeah, this is about means. Is this dependent or is this independent?
Independent.
Yeah, these are independent because this 13 and this 16, they have nothing to do with each other. They're different students. They're not paired up or anything like that. It's just one group and another group. So that means we're going to say mu, and then let's call it M for male, is equal to mu, and let's call it F for female. And then H1. Okay, so now we're gonna have mu, M for male. And then the key word to tell us what the inequality is
Less.
less. Okay, so we have less, so that means we use a less than. Again, I don't try and trick you. You just have to read the word. Mu sub mu F. Okay, we need to write down the test statistic and the p-value. I'm going to copy it because I'm going to need it. Let's go back to the calculator. And what number is this one?
$17.
Yep, 17. We decided it was independent samples. And we have data. So I copied it. So now I pasted those in. Let's go to data 2. Data 2 were these guys. Copy and paste them. We had a less than. This is not a confidence interval question. So hit calculate. There's our test statistic, negative 0.29. And our p-value is 0.39. Any questions on that? Okay, we need to state the conclusion in the context of the study. So what do we say? The p-value is 0.39.
Statistically insignificant.
Yeah, there is statistically insignificant evidence to conclude that the population mean. You didn't have the word population when you had to do a hypothesis test on the exam last week. I took a point off, just to let you know that. And I warned you I would. And if you did have population, I gave you a point. So, it's both sides. So the population mean, and then let's read what we're talking about. We're talking about the time that working with each student for male. Time working with each student for male counselors is less than the population mean time working with each student for female counselors. Any questions at all on question 2 of the quiz?
Will you mark us off if we used a different number of decimals than you did?
No, as long as you follow the rules of rounding, then that's good. Okay, I mean, if you wrote, negative, if you wrote negative 0.8, then that's not good. But yeah, if you use more than 2 decimals, that's fine. So, but you should follow the rules of rounding. But yeah, don't mark you off for the number of decimals. I try not to give you questions where the answer is really close to the level of significance, so that it would matter, how many decimals.
I just wanted that one question answered that was quick yes or no.
Yeah. So number of decimals is, but I know you want quick yes or no, but you are marked off if you don't do the number of decimals they asked for on the homework assignments. So not on the quizzes because I grade it, but the computer's not smart enough to do that. Okay.
Yes, I'm aware of that.
Oh, good. Okay.
Thank you so much for that.
I want to let you know about the computer part because the computer, again, it's not quite as smart. Okay, so number 3 is how much more time do students spend, with their friends in person than virtually when there's no virus issue? 10 college students were observed one day, and the number of minutes with their friends in person and virtually for each of the 10 students is shown below. Here's in person, here's virtually. find a 95% confidence interval, use a complete sentence to interpret this confidence interval in context of the study.
I
That
have
should
a
be part
question.
B. Huh? Yeah.
Was the C a typo, or was there a second part to it?
Yeah, so I want to be honest with you. Sorry, I'm not perfect.
You're okay.
What I do is before, usually a little bit before, 10 or 15 minutes before the quiz, I read through and make sure it's all right. And I realized I didn't ask a confidence interval question. So this was originally a hypothesis test question. So I switched it, but then I forgot with the confidence interval, there's really only two things to do. So I forgot to I forgot to change the C to a B. So sorry about that.
That's okay.
Yeah, that was not meant to be a trick question. That was just a mistake. So
Okay.
sorry.
I just figured I went with like two parts, so I don't know.
Yeah, and in fact, if you read down here, I fixed it for myself, A and B. So sorry about that. Just like it wasn't meant to not that I put students now because I knew that grammar was better. So, I'm not perfect. I do my best. But I decided I better ask you a confidence interval question. So so now we have a confidence interval. Is this dependent or is this independent? What do you think? Because that we have to know. Are these independent or dependent samples? Okay, one more guess. So notice each person is being watched, and the surveyor is watching, or the researcher is watching how many minutes in person and how many minutes virtually for this first person. The first person had 155 minutes in person and 95 virtually. The second person had 136 in person and 188 virtually. So notice that for each person, there's two answers, and that makes it dependent. Any questions on that? Okay, so that means if we go to our calculator, we're going to go to dependent samples with data. We go find data one. Let's copy it in. We go find data two, which is the virtually. The inequality doesn't matter because we want a confidence interval, but we want a 95%. So C level is 0.95. And I hit calculate. Okay, and this time it's not T and P that we want. It's LB and UB, which is, I'm going to round to the nearest whole number. It's kind of easier. How about -4 to 58? Okay, it's even close to the nearest whole number. So -4 to 58. Any questions on that?
So for part A, you just wanted the upper bound and the lower bound.
Yeah, because that's what the interval is.
Okay.
Yeah, when it's just find the interval, there's an interval and I wrote it down. That's all
Okay,
there
I
is.
kind of just copied and pasted everything.
Yeah.
Okay.
Whereas B, which used to be C, sorry, says use a complete sentence to interpret the confidence interval. I want to highlight this word right here. This is interval, it's not level. Okay. I also promised you that I would always ask you to interpret the confidence interval, and I would not always ask you to interpret the confidence level. So there had to be interval. So don't give me this, if many samples were done, nothing to do with that. This is these numbers, -4 and 58. And how do we interpret those numbers? Any questions on that? So we can say with 95% confidence, we can conclude that, and this is the population mean number of minutes people spend per day in person with their friends is, and now it's important, the negative means virtually is more than in person. So that means is no less than 4 minutes and no more than 58 minutes than the number of minutes people spend per day virtually. Any questions at all on the interpretation here? Any questions?
Wait, so when you're using the calculator, which letter represents the confidence interval that you find?
So LB means lower bound, UB means upper bound. So LB and UB. Does that make sense?
Okay, but you only have one number written down. So,
No, I have two, 4 and 58.
oh, sorry, that looked like a decimal.
Yeah, no, it's a comma. I don't think maybe I can make it bigger, but I'm not. Yeah, I can. Here, listen, I'll make it bigger for you. There,
So
does
it's
that help?
so the confidence interval is the lower bound and the upper bound.
Yeah.
Okay.
Yeah. And so the way I made the calculator is the T and the P are for the hypothesis test, the LB and the UB are for the confidence interval. Lower bound, upper bound is kind of how you read this. Okay. And then data diff, because some other instructors wanted that. That would be if you do the subtraction, you get all the data value differences. But I'm not going to ask you questions about that. Other questions about the quiz? Any other questions? Let me hit submit. That way I have it saved. Okay. So if there's no questions, are there questions about anything else? I just want to let you know a couple things while you're thinking about questions. One is I did grade your exam. Hopefully you noticed that. I wrote a lot of comments. So, you definitely want to look at those comments, see where it went right, went wrong, because what's happening in 3 weeks from today?
Final exam.
Your final exam. So the final is comprehensive. So you have to know about pretty much everything from the class in the final. So if you made a mistake, make sure that you understand where your mistake was so you don't make it again. So that's important. Even though we're not going to, revisit this officially, but the final revisits everything. Okay, or has the potential to. Okay, so that's a thing to note. Okay, so take a look at your comments and make sure that you understand them. If you have questions, you can ask me. Braulio is also always happy to help out if you need some, tutoring help and questions with Braulio. But I'm here for you, and definitely take a look and see how it went and where you went wrong, and don't make the same mistakes on the final. Okay, and if you didn't do that well, it might mean that you need to spend a whole lot more time. That's what it usually means. And that could be by yourself. It could be with me or Braulio. But the point is that, if you want to pass a class and you're at that borderline, you might want to think about it of, whatever it takes for the next 3 weeks to get more hours put in, in practicing. Okay. Just doing problems is a biggie. And if there's concepts you don't understand, is asking questions about them too. But we're here to help. So you need to talk to us and ask. Okay. Doesn't seem like there's any specific questions because there's not much going, and we didn't have that much today. But what we got is the project. And I want to note that the project is due June 8th, which is 1 week from today. And it's due at beginning class, so 3:30, I believe I said it. So that needs to happen. And what I'm going to do is on Thursday, we'll talk about the project, and the hope is that you all have your first draft of the project written. And that way you can ask me questions about your first draft, and I can take a look and, help you out with it. So we're going to spend probably, a chunk of time at the end on Thursday talking about your first draft. Just let you know that. And that's the time to ask questions. And even though it's your first draft and everyone else is, having a different first draft, it helps to hear other people's suggestions also, because you might have the same issues. What I find is similar issues happen. So let me mention a few of the issues that happen so that you try to avoid those before you even write your first draft. One of those is to make sure that throughout the paper, for every single thing that you get, whether it's a test statistic or a p-value or a reject or fail to reject or the standard error, so all of the big ones, or the confidence interval lower bound is separate than upper bound. So for every little item, you talk about how the client will use that item to make a decision. What decision might that client make after seeing that particular item? Okay, and sometimes it'll be similar decisions, but sometimes they'll be very different. Okay, so that's an important piece throughout the entire project.
What is the project anyway? Because anytime we've asked about it prior, you've just said that we haven't learned it yet, and you.
Oh no, I
haven't
talked about it
told
last
me.
week, and I talked about the week before. The project
You've
is
mentioned it. You haven't actually told us what we're doing.
yeah, I did. Yeah, I did. You
Right.
could look again at the video from the last couple weeks, and it's a hypothesis test for the difference between two independent or dependent, that's your choice, means. And you're going to be running, an experiment. You're going to be collecting data. That could be by finding data. It could be surveying. That's up to you. Again, this is not like Project One. Okay, so you can have could even use convenient sampling as long as you admit to it and talk about it. Talk about the bias because of it. That's fine. So again, you shouldn't spend a lot of time on collecting the data. You should definitely do things. The main piece of the project, as I mentioned, is a hypothesis test and confidence interval. So that's the biggie, and you go through every detail of it. Okay, and again, if you go back to the video from a couple weeks ago, you'll see that. And last week I talked about it a little bit more when I talked about chapter 10, because it's really a chapter 10 kind of project. Because chapter 10 brings in what you learned from 8 and 9 and 7 and 6, I guess, too. So you should be talking about all that stuff. There's a big piece on the standard error. That's the chapter 7 stuff. So make sure you get into that in detail through it, both in how it relates to the confidence interval and hypothesis test. So that's important. You should also be looking at your p-value, deciding whether, based on the p-value, whether you would recommend doing another study with a bigger sample size after looking at the p-value. There's a lot of different items. So all those things need to be part of your project. And of course, it's a group project. Okay, so again, the idea is have your draft in by Thursday so that I can help you with it. That's the deal. If you have it done by Thursday in a class, then I'll be able to answer questions. I'll even read through a paragraph if you got one or a few, and help you with it. But if you don't, then you waited too long. And then the idea is that I'll help you with the draft on Thursday, and then the next couple days you can fix things that I suggested. So that's really important for the project. Take it seriously. It's a big part of your grade. So don't just do a one paragraph and think your project's done. That's not going to work. Okay, and again, the focus is confidence interval and hypothesis testing and standard error. Okay, don't focus on the stuff from Project One. You could write shortly about that, but don't put pages and pages on what you did in Project One. Any questions on the project and what to expect and what you're going to have to do? Any questions? So hopefully you all have your ideas set. Of course, your partners, that's important. Maybe I'll give you an example from the other class. Remember, I teach 2 stats classes, same class, but 2 sections. So I just helped a student. Their project's due on Sunday, actually. So I helped a student with theirs, and they're looking at COVID per capita in each county for now compared to January. Okay, thinking that it's better now because we got a vaccine. And they're going to be looking at that by doing a sampling of counties. Notice there's no survey. They're going to go online and find the numbers for 31 different counties that they're going to find. They're actually going to stratify it by red versus blue because that's pretty easy. And that's what they're doing. Okay, and that would definitely be a dependent sample because we're talking about each county has a January reading and a today reading. They picked a day in January and a day today. I think January 1st or 2nd or something. So that's an example that, is an interesting project that someone else is doing. Don't do that one because someone else already grabbed it. But the point is that you're comparing 2 different population means. Any questions? Any questions? Okay. And again, I'm here to help out. Braulio's here to help out. I have office hours. Braulio's got lots of hours. And work with your partners. Get help from your partners too. Any other questions? Okay, if there aren't questions, I'm going to move on to chapter 11. Okay, we're getting towards the end. And chapter 11 turns out to be using a different distribution than any of the distributions we've had. See if you can remember, maybe you can put in the chat box. What distributions have we already had? We've had 4 distributions that we've learned already. See if you remember. You can pop in the chat box. Good. Normal's 1. That's the biggie, most important. And we have some other important ones.
Uniform.
Yep. Uniform's the second one. 2 more.
Bimodal.
But you're probably thinking right, but it's binomial.
Oh.
Is that what you're thinking? Just pretend. Uh-huh.
Sure.
Yeah, we had a binomial distribution. We had 1 more. And the hint is it is the easiest to put in the chat box. You could do it in less than a half second. I don't see everyone doing it. Okay, if you don't know, maybe I'll tell you. The t distribution. Remember, the t distribution was used when you didn't know the population standard deviation. So you had to use that t distribution to make that adjustment to the normal distribution. That was for means. Okay, so we've had 4, but unfortunately, none of those will work with what we're doing today. And what we're doing today is looking at qualitative data. So we're going to be using what's called the chi-square distribution. So first thing, chi is a Greek letter. In fact, I've got it over here. So this is chi-squared. So it's not an X. It's kind of a curly looking X. It's Greek. And it's squared. You just trust me. There's like very, very hard mathematics involved in it. And there's a square that goes on. And one of the great things about squaring a number is when you square a number, then you don't have to ever worry about negatives. Okay, because any number squared is never negative. Okay, any real number. So let me show you a picture. And I want to mention a little like the t distribution, there's something called degrees of freedom, which with the chi-squared has to do with kind of how many different possible answers there could be. So if you were looking at a survey question, say, what month were you born in? Then there's 12 different answers. And the degrees of freedom in that case would be 11, it turns out. Subtract 1. And, or if you asked, what state were you born in? Then, you know, if we're only looking at Americans, there's 50 states. So there'd be 49 degrees of freedom. So this is what the chi-squared looks like with 3 degrees of freedom. And you'll notice, by the way, it is very much skewed to the right, right? Big, high top, and then it kind of slowly goes down. On the other hand, if we move the degrees of freedom to much higher, like 29 or something, then you'll notice that the distribution is still a little bit skewed, but not as much. A little more normal looking. But anyway, there is a chi-square distribution. And as we've seen for all the other distributions, let's say we had this chi-square distribution, and let's say the test statistic was 14, then the p-value is the area to the right of that test statistic. Okay, and then we know what to do with p-values when you have hypothesis testing. Any questions on the picture? And the good news is the mathematics is so hard that you're not responsible for it. Okay, it's brutal. So we're not going to do it, but I just want you to get an idea that there is a distribution. Distributions always have these pictures. P-values is the area. We only have a right tail test because when you square something, there's no negative. There is no left tail. It just stops at 0, whereas there is a right tail. So we only do right tail test. Makes it a lot easier because you don't have to think about the tails. It's always right tailed. Any questions at all on the picture? Okay, if there's no questions in the picture, what I'd like to do, I think that the best way of covering this chapter is not by giving you a bunch of general ideas of the theory. I think really you got to do these by example. So what I'm going to
I'd
do,
really like some of the ideas in the theory. I feel like that might make it easier to understand.
it involves multiple integration and infinite limits.
Not that, I mean like the rules of this particular application.
Yeah, basically it's just that you have a p-value. P-value is low, you reject the null hypothesis. You have a test statistic, which I showed you the picture. That's it. Okay. And there's going to be different types, but we need to see the types. And I'll do that through the example. So we'll get there. But
I feel like that always just makes it so much more confusing then, as opposed to like having an actual like outline of how to do the problems.
Yeah, there's not much to do on these, and you'll see that. There isn't a lot to do. The calculator does all the work for you. That's the good news. I mean, I could tell you, you read it, you write down the null alternative hypothesis, you put in the calculator, and then you write your conclusion. That's it. Okay, it's the same as all the other hypothesis tests. There's no new stuff here, other than we're now able to do different kind of problems with this chi-squared. And you just trust me that you can do chi-squared. And I'll show you how the problems are. And in fact, I think I don't want to show you that. So let me give you an example. We'll do a problem and I'll walk you through it. Again, it's not a general kind of thing. Okay, so here's an example. So in California, 39% of residents are Latino, 36% are white, 15% are Asian Pacific Islander, and 10% are other races. Okay, just to let you know, these numbers didn't come from just a survey I did, or I didn't make anything up. I actually did the research, went to Google, and Google found a site that had it. And these are actual population figures. Got it? So this is for the whole population of California. We know what it is because, you know, people have done that kind of stuff. Any questions on that idea? Okay, so now the question is, what about California community college students? So is the distributions of races different for California community college students? Okay, and that's something that we don't necessarily know. Okay, so when you don't know, what you do is you do a survey. And it says a survey was done of 300 California community college students. And 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. What can be concluded at the 5% level of significance? Any questions on the question? Okay, now, as I mentioned, this is hopefully you can read this and know that this is a hypothesis test. Can you all see that? That this is going to be a hypothesis test question. It's not confidence interval. Any questions on that? What is the survey question? Because that's very important when you're doing anything in this class, is to identify the survey question. What was the survey question? What are they going to ask each of these 300 people? It's pretty short. So
What
what's
is
this?
race?
Yeah, what is your race? Okay, so it's really important to be able to do that. And my recommendation is anytime you're starting with any question from the second half of this class, decide what the survey question is, because that is going to get you going in terms of what chapter you're in, what kind of test you're going to be using. Okay, now what is your race? And if someone asked, I might ask the person and they're going to say, I'm a Latino. So the point is that it's not a number and it's not yes or no. Okay, it's a word. And when you have a word answer, we can't do anything we have done before. When you have a word answer, we're going to have to do a chi-squared test. Okay, so that's very important to note, is that chi-squared tests are for these kind of wordy answers in a way. Okay, any questions at all on that? Okay. Whereas if it's a quantitative survey question, then you're going to use something about means, about mu. When it's a question, a yes, no question, you're going to use something with P's. Okay.
Will it always be
Proportions.
specified when you want us to do a chi-square test on something? Like on a test, will like say,
The test will look like what I have right here.
but will it always be specified like you're doing a chi-square test for this?
No, it'll see the example. You reading it? It'll look like this. Does it say chi-squared test? No.
No, that's not what I mean. Like, you know how in your questions you have like part A, B, and C. Will it specify then if you are using a chi-square test?
Will it say, will it specify? Will you ask you to specify? Maybe I'm not following.
Will you specify if you're asking us to do a chi-square test?
The answer is definitely not.
So how do we know if we need to do a chi-square test?
This is what I'm trying to say. You think about what is the survey question. And if the answer to the survey question is qualitative, not yes, no, and also not quantitative, then that's where chi-squared tests come in.
So for quantitative surveys, you want us to always do a chi-square test and include that in our answers.
Okay, quantitative is never a chi-squared test.
Okay, fine. Qualitative, so.
Yeah.
Why are you bloody smiling?
I'm just smiling.
Like, this is entertaining. I'm sorry.
I'm just smiling. That's all I'm doing. You can't get mad at me for smiling. Okay, for qualitative studies, we're going to use chi-squared tests. And as we'll see, we're going to have three different types of chi-squared tests.
In every qualitative study, in every qualitative question that we do, will you have us do a chi-square test?
Yes, and there's going to be three types of chi-squared tests.
Okay, great. That's what I wanted to know.
Yeah. There's going to be a chi-squared test for qualitative studies. Okay, for a hypothesis test. Yeah. And I'll let you know, question number 1 on the final exam is matching. Okay, is a multiple choice. So all I'm going to do is give you the paragraph and you're going to decide what test, and that's it. And then you move on to the next. You're not even going to do the test. So that's a big, and not just question 1, but it's question 1, 2, 3, 4, 5, 6, 7, and 8 or something like that. So I ask you a bunch of questions on matching. So you need to know how to do that, because now we're getting more and more tests, and we're going to get more Thursday. We're going to get more next week. We get another one week after that. We have a lot of tests. So a big part of this class is knowing which test to use. So I want to emphasize qualitative means chi-squared, but it's not just chi-squared. We're going to have different types. And because chapter 11 has 3 different types. And that's what I'm getting into now. Okay, so notice, so the first thing is it's qualitative. So that means it's not a chapter 9 or chapter 10 question. You can't do it with that. Instead, what we can do is we can do what's called a chi-squared test, but there's more to it. You'll notice that this first sentence gives us the population distribution that is known. And then we have a different population distribution that is unknown, and that's the California Community College students. And we just have a sample for them. So we have one sample, and we're comparing its distribution to the population's distribution that we do know about. And when you have that, we're going to do what's called goodness of fit. So that's very important, is that we will use a chi-squared goodness of fit test. Okay. And it checks if an unknown distribution fits a known distribution. Any questions on the idea of what we need to do? Okay. So now we go about doing what we're used to doing. What is the next step once you've decided what your strategy is going to be? What's the first thing you write down? Hint is a letter, a number, and a symbol. So what's the first thing we write down? You all know it. You do it on the first exam. I mean, on the second exam. I'll see you typing it in. Remember? H naught colon. Okay, whenever you do a hypothesis test, you start with H naught colon. Okay, now I want to give you a little word of caution. And that is in chapter 9 and chapter 10, after you wrote H naught colon, how many words come after that? Hint is it's a very easy answer. For chapter 9 and chapter 10, how many words? Three? No. You might be thinking, right? It's easier. That's a hint. 0. There are no words. It's all symbols. So I want to warn you that when you get a problem with chapter 9 or 10 on the final exam, and if you write a hypothesis, an H naught and H1, and you put any words in, I don't give you the credit for it. Okay, it's got to be done in symbols. Okay, and the reason why I'm reminding you about chapter 9 and 10 is in chapter 11, things change. Okay, in chapter 12, we go back to symbols again. But chapter 11, we're going to write things in words because it doesn't really work in symbols. And let me write down the words here. And that is the racial distribution distribution of California community college students is the same as the racial distribution for residents of California. Any questions on H naught? So again, when you go back to 9 in chapter 8 and 9, chapter 9 and 10, don't use words, use symbols. Because that's a big mistake I see, is that once you start getting used to words, you want to use words for everything, and that don't do that. Okay, only in chapter 11. Okay, and it turns out the last half of 13, but we'll get to that another day. Then we're going to have H1. And the key is I'm going to copy and paste. But it's not going to, it's not, H1 can't be, you know, identical to H naught. What do I change? And the hint is not much. So what needs to be changed? Give you a minute to think about it.
Didn't you just say that 0 words come after H naught and then you have words in there? So
Okay, so let me repeat what I said. For chapter 9 and 10, 0 words come after H naught. And now we're moving on to chapter 11. Chapter 11, there's no symbols. Okay, so that's what I'm saying. Don't get confused. So when you go back to studying chapter 9 and 10, it's back to symbols. Okay, and 12 will be symbols too. But so chapter 11 has words. You just got to get that down. So H1, again, it's not identical to H naught. So what do I have to adjust? Not a lot. This is kind of what you should be used to from hypothesis testing. I don't see y'all jumping in. Okay, so H naught is the racial distribution of California community college is the same as the racial distribution of residents of California. H naught is that it's not the same. So I just put not. Right? Because remember, H1 and H naught are like the debate. Okay. One side of the debate says the distribution is the same. The other side of the debate says, no, it's not. It's not the same. The distribution is not the same. Okay, I want to mention one more main thing. This word distribution is required in both H naught and H1. And if you put the word distribution in H naught and H1, even if everything else doesn't make sense, I'll give you points. Okay, and vice versa. If you don't have the word distribution for this test, then you don't get the points that I would have given you. So make sure that you've got that down. I want to mention again, for the final exam, you are allowed a note sheet, full page front and back. You got plenty of room to write this stuff down. Okay, so if you don't want to have to like memorize it, you're able to put in your note sheet. But if you don't do it, you don't do it. But I recommend putting in a note sheet if you don't have it memorized. So any questions on H naught and H1? So what we're looking at again is this distribution that we don't know, and that is California Community College students. And we're comparing it to the distribution that we do know, and that is the residents of California. And when we are comparing a distribution we don't know to see if it's the same as what we do know, then we use this goodness of fit test. Any questions on that? All right, so the next thing we need to do, and I'm gonna put some spaces in so we can have it on one shot, one page. We'll use the goodness of fit. And what I need to do is I need to make a table. I need to make a table that has all the values. So we have Latino, white, Asian Pacific Islanders, and other. Then we have the observed. The observed is very easy. All you do is you write down what they observed. So we saw that they observed 125 Latinos. So I put 125. They observed 92 whites. So I put 92. Okay, they observed 33 Asian Pacific Islanders. So I put 33. And they observed 50 from the other races. So I put 50. Any questions so far on creating this table? Any questions? Okay. All right. Now I need to do what's called the expected. What we're doing is we're comparing what we observed to what we would expect. And expecting means that if H naught were true, what would we expect the numbers to be? Well, a survey was done of 300 students. So if H naught was true, then the proportion of Latinos for students should be 39% because H naught says that proportion is the same for community college and California. So then what we do is we say, what is 39% of 300? Because again, we would expect 39% of 300 to be Latino. And 39% of 300 is 0.39 times 300, which is 117. Okay, you're always welcome to use a calculator. You don't have to do it in my head like I did. You use a calculator. So it's 0.39 times 300. Any questions on that? Okay, then we go for the whites. Well, whites are supposed to be 36%. 36% of 300, that's 0.36 times 300. And that is 108. So I put 108 for the expected for whites. Then we go to the Asian Pacific Islanders. We had 15% are Asian Pacific Islanders. 15% of 300 is 45, right? And then finally the others. And we see that we would expect to have 10% of other races. And 10% of 300 is 30. 0.1 times 300 is 30. Any questions about creating the table? Okay. All right, so when you're performing a goodness of fit test, you always create a table. That's going to be required. So once you've created the table, then when you have an H naught and H1 and you have your data, hopefully you're used to this by now, go to the calculator. So let's go to our calculator. And I do want to let you know we're getting towards the end. So I put this in the order at which we do things. So we're towards the end. So what calculator number do we use? So what's the calculator number?
$21.
Yep, 21, goodness of fit. So I click 21, goodness of fit. It says type in the values of the observed and expected separated by commas. Okay, then hit calculate. So let's go and see the observed. We're 125 and 92. So 125, comma 92. And the next two were 33 and 50. So comma 33, comma 50. Then I go to expected and same idea. I have 117, 108. Comma. And then the last two were 45 and 30. Any questions? Then I hit calculate. Okay, and it gives us chi-squared, that's a test statistic, is about 19.45. Let's write this out. And then the p-value was equal to 0.0002. Any questions at all on getting the chi-squared test statistic and finding the p-value? Okay, so hopefully you're noticing that it's the same procedure we've done. Again, there's no general stuff to talk about here because it's what we've been doing. You write down your null hypothesis, you write down your alternative hypothesis, fill in a table, get your data basically, that's what that is. And then put in the calculator and get the test statistic and the p-value. All right, what's important about this p-value? Because that's our next step in hypothesis testing. Yeah, it's less than, and not only is it less than 0.05, it's less than any level of significance you'd use. So in particular, it's less than 0.01, which is about as low as anyone typically goes. So we can definitely say that if it's less than any level of significance, what's the conclusion? What's the first words, at least? First few words. You're used to this from last few weeks? It's the same first few words you used before. Yeah, there is. And then the next two words?
Statistically significant.
Statistically significant evidence to conclude. And now what I do, since I've already got written out, is I can copy and paste H1 and then adjust the grammar a little bit. So that probably is best. And then lowercase the. Racial distribution doesn't need to be read anymore. We've dealt with that. Of CCC students is not the same as a racial distribution of residents of California. And that is our conclusion. Notice, by the way, when we went to the calculator, it didn't even ask for whether it was less than, greater than, or not equal to. That doesn't happen with chi-squared. You only have the right tail test. So that's all there is to it. Let me note something, and that is that's all you can say. Okay, what we can't do from the chi-squared test, we can't say, well, yeah, the distribution is not the same, but can we say, well, that's because, the other races is, over, there's a lot more other races than there should be. Okay, you can't go and specify which is the reason that the distribution is different. Yeah, you can't do that with chi-squared. And I will let you know, we're getting kind of towards the end of the class, so I can start talking about this more and more, is that it can be done, but not in elementary statistics. So if you continue on and take an intermediate or advanced statistics in upper division or graduate school, then you'll learn about other tests that you would do after the chi-squared test to decide, well, not just there is a difference in the distribution, but how are they different? And that we're not doing in our class. All we're doing is saying that the distribution is not the same. Okay. Still curious how you use stats to make 210% in the stock market. Okay, I mentioned it last time, last week. So, and I don't always make 210%, but it definitely make more money than a lot of people. Math helps. Math helps. And it is not from, goodness fit test, by the way. Okay, more standard t-tests for the stock market. Okay, so typically you wouldn't use a goodness fit test for a stock market pricing question, because that stock market prices are quantitative. And when you have quantitative, that's not goodness fit. Okay, unless you're doing ranges instead of the exact prices. But for stock market, you care about exact. Any questions at all on this example and how I proceeded with the goodness of fit test? Okay, if there's no questions, then I'm looking at my clock. It's 5:03. There should be stats for stocks. Yeah, that would be in the business. That would be in the business department. Okay, I like this one for the casinos. It's a little different. Okay, but anyway, I can't do that. Sorry. But I'm looking at it, and it's around 5:03, 5:04. I'm going to stop my share, and I like to give you a break in case you need, 5 minutes or so, and we'll come back in a little more than 5 minutes or so, and then we'll get back and we'll do more examples. Okay, welcome back. So let us continue on. I'm going to share my desktop again. Okay, are there any questions on this example of a chi-squared goodness of fit test? Are there any questions? Okay, if there's no questions, we're going to do another one. And let's look at a different example. It's going to look very different, but very important. Okay, so a study was done asking people how far they traveled this Memorial Day weekend. Okay, the mean was found to be 120 miles. The standard deviation was 40 miles. The table shows the results. Okay, so what we have, I'm going to erase this for now. And there were 56 people that traveled fewer than 80 miles. I was one of them, by the way. There were 61 people that traveled between 80 and 160 miles. And there were 12 people that traveled more than 160 miles. And the question is the distribution normal? So we have actually not answered this question before, but we often talk about it. Okay, because if you remember, when we're doing a confidence interval or a hypothesis test for a population mean, and if your sample size is too small, then you have to assume a normal distribution. And assume is never a good thing. So instead, what sometimes you can do, if you happen to have a similar study of something like it, then what you can do is we can test for a normal distribution instead of assume a normal distribution. Any questions on that idea? Okay, this is a little different than what I said before because the survey question is actually technically quantitative, because you would ask someone, how far did you travel this Memorial Day weekend? Except what we've done here is we've just put it into 3 general categories. Okay, so it's like low, middle, and high. We can look at those 3 categories. So in a way, we've taken a quantitative question and we've made it qualitative. Any questions on the question? Any questions?
How is it qualitative?
Because I can, instead of writing less than 80, I can just say low. And I can call this one middle. So notice now the word answers. And this one high. Do you see that? Where we've defined low to be less than 80, middle to be 80 to 160, and high to be greater than 160. And that turns our quantitative into qualitative. And that's done a lot, by the way. Okay, does that make sense? Any questions on that? All right, these numbers are not just some randomly, provided numbers, 80, 160. Those numbers are important numbers. Anyone see why they're important given the information I gave you in the paragraph? Anyone see the significance, why 80 is an important number and why 160 is an important number?
Also, wait, where did you get the values that you put into the table?
You mean the 56, 61, 12?
Yeah, where'd you get those?
That is just provided that, in other words, that there was a survey done and there were 56 people in the survey that were in the low end. There were 61 in the middle end and 12 in the high end. So that would have been a survey.
Would that be done on a test problem?
Oh yeah. Yeah. And to be honest, I made the values up. But in the real world, what you would do is you would conduct a survey and you would figure out how many people on each end. Do you see that? And that'd be a whole lot of work. But in this class, we don't have time to do that. So I just say, let's suppose we did it. Yeah. On the other hand, the 80 and the 160, those are not just some random values. Those are important. Why are they important? Okay. In other words, had I given you 90, it really wouldn't have made, it really wouldn't have been the right way to do it. Still could be done, but you wouldn't want to go there. Q1 and Q3, not quite. You might be on the right track, but it's not, these aren't quartiles. Quartiles, just let you know, quartiles in the normal distribution, they usually don't go together very well. Usually don't put those together. Any other guesses or thoughts? Something very important about the number 80 and 160, those two numbers. All right, if you're not guessing, what is a z-score for the number 80? So again, let's think back to, the first week of class. What's the z-score for the number 80? The hint is it's very simple, very nice. Don't see y'all jumping in. Remember the z-score formula? You take the x minus the mean divided by the standard deviation. What do you get? What's 80 minus 120, all divided by 40? Yeah, it's -1. What's the z-score for 160? That's even nicer.
Wait, why do we need the z-score?
I'm giving you a hint because no one's seen the importance. So now I'm showing the importance. The z-score is 1. So this middle range means that the z-score is between -1 and 1. What percentage of the data, if it's a normal distribution, should have a z-score between -1 and 1? See if you can remember. What percent has a z between -1 and 1?
So for problems like this, do you need to find the z-score?
For this problem.
But for problems similar to it, do you also need to find the z-score?
Yeah, if I asked you, is it a normal distribution? Okay. Do you remember the empirical rule? That's a hint. And it's been a while, but it's part of the class. Do you remember the empirical rule? I know it was project 1, so it's been a while. Yeah, 68%. So what that tells us that we would expect 68% of the data to be in the middle range, because that's what the empirical rule tells us, is that the 68% of the data, if you have a normal distribution, is in between, has a z-score between -1 and 1. That was the empirical rule. So now we just go and we say, well, how much data is there? Well, we have 56 plus 61 plus 12. So let's do that. So notice that 56 plus 61 plus 12. Well, that's what, 117, and then another 12 is 129. Again, you can always use a calculator. Okay, that's our sample size. And then we can say 68% of that is 0.68 times 129. And that's the end of me being able to do it in my head. So let's go into the calculator, or at least do it in my head fast. And 87.72, I'm going to round to the nearest whole number since this is a number of people we expect. So 87.72 becomes 88. And that is what we'd expect if we have a normal distribution, and that goes right here. Any questions on how I arrived at 88? Okay, so to find out how many should be in the low, well, the idea is we have 88 that should be in the middle. So if I take 129 minus 88, then I get, so 12 and 29 is 41. And I get 41. Okay, any questions on that? Okay, so now if I take 41 and divide by 2, because half should be in the low and half should be in the high, I'm just going to round that to half of 41 is 21. 20.5, I'll call it 21.
Will these distributions of the percentages always be the same?
Well, that's the empirical rule. The empirical rule says that 68% of the data within a normal distribution for between a -1 and 1 z-score is always 68%.
So is this problem just asking you to determine whether or not the data presented in the word problem is normally distributed?
Yep. Yep.
Okay, so you're just saying whether or not it is normally distributed and proving it with the table.
Right, and here's the question right here. Is the distribution normal? Do you see that?
I'm just trying to make as much sense of this as possible.
I'm highlighting the part that asks you about the normal, and it's right there, and that was in the question. So the first is O for observed, the second is E for expected. Any questions? Any questions? You see how that works? Okay, so now we can actually get our null hypothesis, H naught. H naught is going to be the distribution. Remember, it has to have the word distribution. Of travel time is normal. Any questions on that? Okay, and then H1, I always like to copy and paste and then change what I need to change. And that is what? What do I have to add in to get an H1 out of it instead of H naught? Very simple. Yeah, so the distribution of travel time is not normal. Any questions on that? All right, well, this is a goodness of fit test. Note this is goodness of fit. Since we want to see if an unknown distribution okay, and again, the unknown distribution is the distribution of travel time is the same as a known distribution. In this case, the known distribution is normal. Any questions at all on this example so far? Okay, the rest is actually pretty easy. I think the hardest part is to realize that this is goodness of fit and then to come up with the expected vet counts, because that took some thinking. Okay, then the rest is just calculator work. So now I'm going to go back to the calculator. My observed, of course, is not going to be the same. The expected is not going to be the same. We've got new observeds. So the observeds were 56, 61, and 12. And the expecteds were 21, 88, 21. Any questions on that? Then hit calculate. All right, our test statistic is 70.47. Let's write that out. Then the p-value is the p-value equal to 4.44 about? Yeah, be very careful. P-values can never be bigger than 1 because they're probabilities. Probabilities can never be bigger than 1. If you ever write a number that's bigger than 1 for the p-value, you blew it. It means you didn't read the whole thing. See that e negative 16? That means we got to move the decimal over 16 places. This p-value is minuscule. Okay, and the way you usually write it in research is you just say p-value is less than 0.001, because anything less than 0.001 is always going to be treated the same way. Okay, it's much less than 0.001, but it's definitely less. Any questions at all on finding the test statistic and the p-value for this particular example? All right. Can you show the calculator again? Sure. Let me get there. There's not much to it. I just put in the observed numbers separated by commas, the expected numbers separated by commas, and then I just hit calculate. And there's my test statistic, and there's my p-value. That make sense? One of the great things about chi-square tests, there isn't much to them. Okay, there's not a whole lot of stuff you put in. You just put in the observed and the expected and gives you a test statistic and p-value. There's no confidence interval. There's no left tail, right tail, two tail, not equal to less than. None of that stuff is needed. Chi-square tests are very simple in terms of what you have to put in. Is just the data and that's it, and calculate. So it's definitely the easiest of all the tests that we've got in this class. Okay, the underlying math that I had to put in the calculator is not easy at all, but you don't have to worry about it. Okay, so it's time to do our conclusion. And that is what? How does it start? For a few words, you should be used to this by now. Yeah, there is. Okay, and is it statistically significant or insignificant? That you should know also without knowing anything from this week. Yeah, significant. Statistically significant. Evidence to conclude that. And all I do copy and paste H1, maybe change the grammar a bit. Make that the lowercase t, that the distribution of travel time is not normal. Okay, so in this case, assume normal is just bad. You shouldn't do it because we just showed that it's not normal. Okay, we have very strong evidence that it's not normal. Don't even think about assuming it's normal. So if you had to do, if this were truly the case and you had to do a study and you did another study of maybe 20 people, asking them their travel time, you can't do anything because we definitely know very strong evidence is not normal. So don't assume it's normal when you know it isn't. Any questions on this example? Okay, I do want to let you know again, this is a test for normality. There are more precise tests for normality, but that goes beyond this class. That would be more of an upper division course called the Kolmogorov test for normality. We don't do that. But I just want to show you kind of a basic test for normality, which is much better than looking at a histogram and eyeballing it, because that's not very mathematical. You really need a test. All right, let's do a third example. Okay, and it's the following. There are 3 shifts in the emergency room, morning, afternoon, and night. Okay, does the emergency room get the same number of patients for each shift? Over several randomly selected days, the number of patients that came during each shift was tabulated. Here it is. All right, what is a survey question? What are you going to ask the patient? So what would the survey question be for this? Yeah. Yeah, did you go to the ER in the morning, afternoon, or night? And the person's going to say afternoon. They're not going to say, 3. They're not going to say yes. They're going to give you a word. So we're in that category of qualitative survey question. Okay. So that's what we're in. So what we need to do is we need to think about, first thing is, based on the question, what distribution are we trying to fit this to? Or we're seeing if it fits in one word.
Uniform?
Yeah, this is uniform, because if you get the same number of patients for each shift, that means you have a uniform distribution. So I'm going to write H naught, and that is the distribution of patients in the emergency room and maybe the distribution of shifts. Maybe I should say for the 3 shifts. Is uniform. Any questions? Any questions on H naught here? Okay, so what you're always doing with this, good as a fit test is you're seeing if an unknown distribution fits a known distribution. So this is a case where the known distribution is uniform. And we want to say, is it uniform? The nice thing is that H naught is really easy. H1 is really easy. So I can copy and paste. Turn that naught into a 1. And what do I have to do? Yeah, not uniform. Okay. And by the way, the way something like this would be used is if you were the manager for the emergency room, then you're going to have to decide, how many nurses and doctors are you going to want in the emergency room, working in the emergency room for the 3 different shifts. And if they're uniform, you're going to hire the same number of people for each shift. Whereas if they're not uniform, then you got to deal with it. And then you got to figure out which one's more and how much more and all that kind of stuff. But if they're uniform, it's really easy. It's the not uniform is the issue. Any questions on that? All right, the next thing we need to do is we need to figure out what the expecteds are. So I have the observed, call that O. We're going to have expected. Let me give you a minute or two. See if you can figure it out. I'll be quiet for a bit. And let's see if you can figure out what the 3 expected values should be. And it shouldn't be too hard. You might need a calculator. I'll give you a minute, a couple minutes. Okay, we got one guess. See if anyone else seconds it or has a different idea. I don't see y'all jumping in to say Jack to say the first attempt was right or not. Hopefully you can. I'm waiting to see if somebody seconds your answer.
There's nothing in the chat.
There's one thing in the chat. We got one answer, and I want to see if someone else can come up with the same or has a different idea. As I'm looking in the chat. Okay, so we actually, now that I look at it, the one attempt was a message to me, not to everyone. So seconding it doesn't make any sense because you don't see that number. So I want to hear what you're seconding. I want to see what number you think it is. Okay, if you don't know, maybe I'll go and do it. Okay, so we'll see. So let me tell you the direct message to me instead of to everyone, by the way, which is okay, was 131. Let's see if that works. So the idea is that if it is uniform, then they should all be the same. I'm going to counts. So let's look at the total. Let's go over here. So I can put it on the same page. So the total was 123 plus 159 plus 111. And I could put that in the calculator. And it gives me 393. Any questions for getting the total number of people, the N, the sample size? So maybe I'll write N equals because that's what it really is. Any questions on that? All right, well, if it's uniform and we have 3 different shifts, how do I find out how many we'd expect each shift to have? Yeah, we divide by 3. So our expected is going to be 393 over 3, which actually is very easy when I can do my head because I divide each of them number by 3, and I get 131. And that is what the one person who put in the chat box to me personally said that it was. So nice job. Any questions so far? And again, this is about being uniform. So about being uniform means all 3 of them are 131, not just one, one of them, but they should all be the same. Any questions on that? All right, well, now that we have our observed, we have our expected, we have our null hypothesis, and we have the alternative hypothesis, the next thing we can do is go to our calculator. And again, today is goodness of fit day. Just let you know, on Thursday, we'll do the other 2 tests. Goodness of fit tends to be the most complicated because it has different types, kind of the previous to now, the normal, and the uniform. Whereas the other 2, there's really 1 type. So that's why I can do two next time and 1 this time. So just let you know that that's the plan, is that it shouldn't take too long to do the other 2. So let's go ahead, and our, of course, observed and expected will not be what we had for the last example. So our observed, we had 123. One, 2, 3, comma. And then we had 159, comma. And then we had 111. The expected were 131 for all 3 of them. So I just type in 131, comma, 131, comma, 131. Any questions on getting the observed and expected and inputting them into the calculator? Okay, then I hit calculate. And I get a chi-squared of 9.53 about. So let's write this down. Test statistic is chi-squared is equal to, and again, that was 9.53. And then the p-value was equal to 0.009 is good enough. So now that we have the test statistic and we have the p-value, we can state our conclusion. So what's the conclusion? How does it start? So how does it start? The conclusion? Yeah, there is statistically. And is it significant or insignificant? There is statistically, okay, we have a small p-value, and we have a small p-value, we have significant evidence. Okay, it means we got what we wanted. To conclude that. And now what I do is I copy and paste H1. And make the lowercase, that the distribution of patients in the emergency room for the 3 shifts is not uniform. Okay, can we look at this and say that with the distribution, the reason why it's not uniform is that there's just a whole lot more afternoon people that come in? Can we say that? Because 159 is definitely bigger than 131. What do you think? Would that be valid?
Sure.
One more guess?
No.
No. As I mentioned, all we get from a chi-squared test is the distribution's the same. The distribution's not the same, or there isn't evidence to show the distribution is the same, is not the same. You can't say what's the reason why the distribution is the same or not, why the distribution is not uniform. You can't say it's the afternoon shift is the reason. You can't say that the night shift is the reason because the night shift is too low. You can't go there. Okay, to do that, you need to take a more advanced statistics class. In our class, we stop at the distribution is not uniform. We don't try and get into the details of why it's not uniform. That we can't do in this class. You can't do that with a chi-squared test. Okay, there's something called a Tukey analysis that you can work on. There's some other tests also that work, but we don't do that in this class. Any questions at all on the process? Again, the process always is, hopefully you all know this by now, read the question. Always the first step is to read the question. Then once you read the question, you strategize. Okay, and strategizing means you decide what test it is. One of the main things you want to do is say, what is the survey question? If it's qualitative, and if you want to find out if the distribution of a samples population is some distribution you do know of the population, then you can use goodness of fit. Then you state the distribution of whatever you're looking at is uniform for H naught, or is normal, or is the same as something known. And H1 is the distribution of whatever it is you're looking at is not uniform or normal or the same, whatever it happens to be. Okay, then what you do is you calculate the expected counts. Okay, you make a table, you put in the observed, that's usually easy, that's just typing in what they gave you. And then you calculate the expected. If it's a uniform distribution, you take the total and divide it by the number of choices. And that'll be your expected for all of them. If you're talking about a normal distribution, then we're going to use the empirical rule. If you're talking about some known distribution, you're going to use the percents known and multiply by the sample size. Whatever it is, you're going to get the expected. Then what you do once you have the expected is you put it into the calculator. You get your test statistic, which is chi-squared. You get your p-value. Then you look at the p-value and decide is the p-value less than the level of significance. And in the real world, no one gives you a level of significance. So typically you just look at it. In fact, you could even say there is strong because we have less than 0.01. There's strong statistically significant evidence to conclude that. And then you write down the distribution and you basically rewrite H1. Okay, and that's it. And by the way, if our p-value instead of being 0.009 was say 0.47, then it would be exactly the same, except right here where it says significant, you'd write insignificant, which means you really don't know anything. Significant means you've got it and you can publish it, use it. Insignificant means you don't really know anything. So that's the process of the chi-squared goodness of fit test. So I am looking at the time and it is about end time, which is good because I wanted to finish goodness of fit test. So I'm going to stop the recording.